Alright folks, Chapter 3 is all about functions, so we are going to review all the parent functions you learned in Algebra 2 before moving on to things like transformations of graphs. So what we're going to do on your worksheet here, you'll see there's a space for you to write the equation. Above that, I'd like you to write the name of all these parent functions as we go through them. So first up is identity. So write that. We're most familiar with it called a linear function or a line. Okay, but identity is your parent function. And your equation for that is y equals x. It takes your mx plus b and it simplifies it, getting rid of all the extra numbers. Okay, and based off of that, we're going to start our sketch at 0, 0, going through the origin, and then our slope is 1, so you're just going to draw a line increasing to the right. From that sketch, we're going to answer questions about the domain and range. So domain left to right, all real numbers are popping up here. Same thing going on for the range from the bottom to the top, all numbers on the graph show up. Next up is the absolute value. And the parent function for that equation is y equals the big bars with x inside. The shape of this actually looks like a line on one side, and then the other side, instead of going down when we go to the left-hand side, those negative x values, it ends up going up. That's because when we talk about an absolute value, it takes your negative values and changes them to the positive version. Again, we have the point 0, 0, so go ahead and label that on your sketch. Domain left to right, we have all real numbers again, because it's okay to take the absolute value of any number in the world. But when you take the absolute value of any number in the world, all your negatives go away. So lowest number here is 0, that's included, we put a bracket, and then we keep going towards positive infinity. Next up, we're going to talk about the cubic function, and you haven't seen this really a lot. Parent function is y equals x cubed, and the shape of it kind of looks like a parabola on the right hand side. If we think about a parabola, you know it makes the shape of a U, and it's just because you're squaring those numbers, they get larger and larger as they go to the right. With a cubic, same thing happens, they're getting bigger and bigger. You're cubing them as you go to the right. What's different for this shape is as you go to the left, when you cube a negative number, it stays negative. Negative times negative times negative. Whereas with the parabola, it switches. Okay, so we're going to start low, make a little snake shape going through the origin, and end high. Put a point on 0, 0 for me. Because we go all the way through the graph, domain and range are both all real numbers again. Next up is an exponential, and we've talked about this year already, but our parent function is y equals, we're going to write b to the x, and this b is important because we're going to fill in some number here when we're talking about it. So our parent function is going to have something like y equals 2 to the x or 0.5 to the x, but that number is going to be filled in when we talk about it. We're going to go ahead and sketch growth because it'll answer the questions just like decay would. So start low at the x-axis, then increase as you move to the right for me. We're starting at the x-axis because there is a horizontal asymptote at y equals 0 there. That's important to our graph just like our starting point is. For an exponential graph, we're not at 0, 0 because of that asymptote. Instead, if you recall, our y-intercept is 0 and then whatever the a value is in front. If you don't have a number in front of whatever your base is, then that value would just be 1 here as your y-intercept. Domain, we hit every x value. It's okay to have anything as x in a power. But when we're putting numbers in there based on our restrictions for what the base can possibly look like, we're never going to get 0 or any negative numbers out. So we're starting at 0, but we're putting a parenthesis to say that's not actually included, and then going up from there. This next graph you have not seen a whole lot but they did talk about it in Algebra 2. It's called the greatest integer function, or a step function. Name comes from what the graph looks like, kind of like a staircase. Your parent function looks like y equals, and outside of this x, or around it, you've got the brackets that look similar to an absolute value, but then there are feet on the bottom there. Okay, those tell you what direction to round your number, but it's all about rounding. When it says the greatest integer function, it says you're taking all x values that you plug in and then rounding them down to the integer that is below it. So if we look at our staircase again, you'll notice on the left-hand side of all of these stairs you've got a closed dot, and on the right-hand side you've got an open dot. When we think about the spaces in between, you'll notice when we're going through here, we've got a marking at 0, we've got a bar at 1, another at 2, another at 3. It's at the integers. So the greatest integer function gets its name from what happens on the picture. What I want you to do is just start with 0, 0 as a point, and then to the right of it you're going to make an open dot, and then you're going to repeat this just by shifting it up and over. So above that open dot you're going to put a closed one. Those were not intended to be connected there. There we go. And then open one to the right, and repeating that as you keep going. After that, just throw an arrow on to say that'll keep going, and we'll do a couple on this side as well. So below the closed dot you've got an open, close to the left of it, and then one more to the side. Because if you look at this graph, the solid dots line up with the open dots, every number is covered. But again, think of it as, instead of what's happening on the graph, what's happening on the equation. Domain just tells you what's okay to plug in. You can round down any number. That means all real numbers is your answer. The range values, though, are what pop out when you round them down. Well, you're rounding them to an integer, so our range is all the integers. And how we write it is actually with set notation. You're going to start with a set bracket. Range is y, so y such that y is an element of, hopefully that E symbol is familiar, and then double bar z is our integers. Next up is a hyperbola. We talked about this last chapter as well. Parent function is y equals 1 over x, and because of this x in the denominator, we have a restriction in our domain. You can't plug in every number and it be okay, because if you plug in 0, we're taking 1 divided by 0, and that's a problem. That shows up as a vertical asymptote on our graph. You're going to write x equals 0. And then because we can only plug in positive numbers or negative numbers, not 0, you're also not going to get a 0 to come out for the y values. So we've also got a horizontal asymptote at y equals 0. Okay, the shape of this is determined by how this function looks always. But let's talk about it for a minute. On the right-hand side, you've got your positive numbers. When you plug in positive numbers, you get a positive result. So all this branch lands in quadrant 1. Similarly, when we plug in negative numbers over here on the left, you're taking positive 1 over a negative number, you end up negative down below. So you're going to use these asymptotes to guide you. Start at the asymptote and end at it, and you just match that curve. This is the shape of a hyperbola, but on top, if you would, we're going to actually call this an inverse. Okay, the shape is a hyperbola, but the parent function's name is an inverse. That's why this next one is called an inverse square. You'll notice the denominator is x squared instead, so parent function 1 over x squared. And because of that squared, the second negative half switches. When you plug in negatives and square them, they end up being positive. We still have the same restriction in our domain as the last one. X can't be 0. And because it can't be 0, y also can't be 0. We're going to start at the branch, or start at the asymptote and end at the asymptote. Same thing on the other side. Alright. Talking about domain here, we don't have all real numbers. We already talked about we're leaving x out, so, or 0 out for x. So negative infinity to 0, union with 0 to infinity. And then the range here, we don't have any of those negative values, so we're actually starting at 0 and going on to infinity. That's different than this last one. Sorry, I missed it here. We're going negative infinity to positive, or to 0, union, 0 to infinity. But on the range, you do have negative values show up. So it actually looks the exact same as the domain, negative infinity to positive infinity, leaving out that 0 value. All right, we've got our parabola. This one we have seen for a long time, y equals x squared, starting at 0, 0, and makes a parabola shape after that. The name of it itself is quadratic. The shape is the parabola. Then our domain is all real numbers. We know that because we can square any number in the world. And when we square stuff, we're starting at 0 and going bigger from there. Go ahead and put that 0, 0 on your graph, just like we have been. And our last one here is the square root function, y equals square root of x. Because this is talking about taking the square root of a number, you'll notice on our graph it starts at 0. That's because everything to the left of it would be negative, meaning the square root of a negative value. And we can't graph that because the only way to take a square root of a negative is to involve the imaginary number system. Okay, so we're starting at 0, 0. When we take the square root of something and it says square root, we're writing only the positive answer. Okay, that's different than when you're solving an equation and you do the square root. When you see the square root, automatically you just go with the sign you see. Okay, so positive is what we're looking at here. And based on that shape, our domain is starting at 0 going on, and same thing with our range. These points and asymptotes are going to be important for us to determine the shape of graphs and how we can sketch things. Once we get to know these parent functions, we won't have to type as much into our calculator to be able to answer questions. We're going to practice a little bit with that on the back side here. It's going to ask you to identify all the critical values algebraically, and the purpose of this down the road is so that we can make sketches without using our calculator. Okay, so what I want you to do for each of these first is identify what parent function it goes with, and then make a little sketch of the shape. So here we've got the absolute value marks, so you can go ahead and write the name of it, absolute value. But more importantly, we care about the shape of the graph. An absolute value, because all positive, it makes kind of this V shape. And when we're talking about critical values, the ones that come to mind for what we've been talking about are x-intercepts, y-intercepts, maximums, minimums, and asymptotes. So here, most graphs are going to have at least one of each of these, but we also have to look at the shape to determine if there's anything special about it. So the special point on this graph is our minimum, or the vertex of this absolute value. And that point we're actually going to find first for all of these graphs. And the reason we're going to find that first is because it's easily seen by the formatting of our parent function here, or a transformed function. If you recall from Algebra 2, you had what was called a generic function, and it said we can write transformations of graphs if we can recognize the transformations using the common ones that show up. So how they wrote it is a on the outside, then bx minus h inside, and they used parentheses, and then plus k outside. And these parentheses could be replaced with any parent function. In our case, we're using the absolute value. Now, all the ones we're going to look at to start with are only involving h and k. We're going to spend more time talking about a and b later. But h and k talk about translations on a graph. You'll notice it says -h. That means whatever you see here is the opposite of the h value, or the horizontal translation on the graph. Then it says +k, meaning the number you see is the number you get for the vertical translation, up and down. So when we see +25, that means left 25, and when we see -10, that means down 10. Why that's important is because this original point started at 0, 0. If we can take that point and translate it, we just found the new critical value without a lot of work. Okay, so this, like I said, was called the minimum, but it's also called the vertex. And we just decided it's at -25, because left, and -10. Once you have that point, we're going to do the x and y intercepts. Y-intercept's actually the easier one because of what it looks like on a graph. Remember, a y-intercept is just where the graph hits the y-axis, and that ordered pair is always 0 some number. So that's how we find it. We put 0 in the first place, which means our x value is 0. We just go up here and place 0 in the place of x. So that says take the absolute value of 25, we know that's just 25, -10, and you get 15. You may write yourself a note of what you did there so you don't forget. Just substituting in. Usually the more challenging one is the x-intercept. We've seen that with quadratics, but it honestly depends on the parent function. What we're going to do, kind of to think about what's going on here, I'm going to take a time, and I want you to do this as well. We started out with our shape at 0, 0. We're going to make one more sketch using this to kind of get an idea of what should happen on our graph. So our vertex was -25, -10, and then from there we have this V shape. So you'll notice our y-intercept, we had one of them, we already found it, and you can see we have 2 x-intercepts. That'll kind of give you an idea of what to look for as we go through this process. So x-intercepts, just like we were talking about on the y-axis, the x-axis always looks like x and then a number 0. So what we're going to do is go back up to our equation and do that. So 0 equals, and then starting with our x plus 25, then we have a -10. Now, to solve something like this, the whole idea is to get the x value. We just try to get x by itself the old-fashioned way. Okay, so we're working through order of operations backwards, which means we got to get those grouping symbols by themselves. We're adding the 10 over to the other side. Okay, at this point you want to pause and ask yourself, is this possible? Can you take the absolute value of something and get a positive 10? Of course you can. But if you ever saw a negative here, taking the absolute value of that would not be possible. A graph like this, if you ever got a negative over here, would be something strange happening from the original graph, like the whole thing floating above. That would indicate there are no x-intercepts because you couldn't solve that absolute value. As it is, we know there's supposed to be 2 answers. That's because we can split this up into 2 separate pieces. Here's how it works. The first one, we're just saying that this has to equal 10. So we write x plus 25 equals 10, and we go solve it. Subtracting that over, we get -15. The second thing that could happen, though, here's what we're really saying. We're saying the absolute value of 10 we know is 10. But there's another possibility. We could also take the absolute value of -10 and end up with a positive still. So for the second piece, all you have to do is take what's inside those brackets and set them equal to the opposite of whatever number you started with. Once you have that, same thing, we're just solving by moving that over real quick. So x equals a -35. And those are our 2 x-intercepts. We'll just plop them next to each other. So -15, 0 is our first one, and -35, 0 is our second one. You're always welcome to check your work in a graph. Okay, we're trying to get to a point where we know the shape of these from the parent function and get an idea of what should show up on it. Next one here, again, first step is figure out the parent function. Ours for this one is a square root. And it looks like usually starting at 0, 0, going to the right. We know we're going to have to look for x-intercepts 1 or 2, y-intercept 1 or none, and then when we're talking about the last piece, it's based on the parent function. So for this, it's another minimum, or this is actually called the end point. You can always call it the minimum or the maximum for things like that, but it is called the end point, and we're going to find that first just like last time. So thinking about this, we've got a plus 9, so we're going left again, and we've got a minus 10, we're going down, or a minus 5, we're going down. So from 0, 0, let's go ahead and do ourselves this favor so we can work with those ones as well. From here, we're going left 9, down 5. We'd have something like this, and up and to the right. So most likely we'll have one x-intercept and one y-intercept. There is a possibility that we hit it at 0, 0, where the x would be the y-intercept. Not sure where it crosses over at this point. That's what the math will help us for on those. We do know the end point, though, and we'll write it as our negative 9 and then negative 5. From there, we're working our way backwards. Y-intercept, remember, you just plug in 0. So 0 plus 9 is 9. We're taking the square root of that. I'll write some notes here to the side. So square root of 9 is 3. 3 minus 5 is negative 2. So my sketch here was off because it didn't quite go as steep. Would look like something like that. Instead, we ended up having our y-intercept at negative 2. We're still going to cross that x-axis at some point because it does increase forever. So x-intercept, we're putting a 0 in for y. And for that, usually there's just a couple extra steps. So wherever you've got some space here, we're going to plug in 0 for that g of x. And then we've got square root of x plus 9 minus 5 goes to the side. Grouping symbols are important just like the last time. To solve for x, we have to get that grouping symbol by itself. You're moving it over. So you've got 5 equals the square root of x plus 9. Again, you have to make sure this is possible. When you take the square root of something, when you see it, not when you made it, it should be a positive number. If this was ever negative, it's because your graph wouldn't have been anywhere near this x-axis to cross over. Okay, so watch out for that. But at this point, we're trying to get rid of that square root, so all we have to do is square both sides. So this becomes 5 squared is 25. Over here, those cancel, x plus 9, and you can see we only have one answer. All we have to do is subtract that 9 over. So x equals 16, and that's our x-intercept, 16, 0. Last one we're going to do here is parent function 1 over x minus 5. This is just regular x, so this is our inverse. It takes the shape of a hyperbola. Remember, we have asymptotes. When you make the sketch of these, please write the asymptotes on there because they are the critical values that we're going to have to list that are special. Branches go opposite directions with the hyperbola, not side by side. And we're going to go to work on finding these items just like on the last one. So set yourself up here. X-intercept, y-intercept, and the special items are those asymptotes. Okay, we have 2 of them, so we're going to label horizontal asymptote and vertical asymptote. Okay, just like the last time, the numbers you see with your parent function are going to tell us whatever that's special about our graph. So in the case of this, instead of moving to point 0, 0, our x shift is going to just talk about that vertical asymptote where it moves to, and our vertical shift up or down is going to refer to what happens to that y equals 0, or horizontal asymptote. So going to here, because this minus 5 is grouped with x, it has to be the left and right, and it's always opposite of what you see when it's grouped. So this minus 5 means to the right 5. So instead of being at x equals 0, I'm at x equals 5 on my vertical one. Horizontal, y equals 0, you're going to see a shift to the side. We don't have anything here, meaning the y equals 0 is still happening. Now let's go to work on these things. The y-intercept, again, you just plug in 0 for the x value. And when you put a 0 here, you're just left with negative 5 on the bottom, so negative 1/5. Okay, the x-intercept, we're going to go to work on with the second value being 0. And again, wherever you have room, we're doing 0 equals 1 over x minus 5. These two terms are going to be important that we group them together. So put parentheses around that. Anytime you've got a fraction involved and there are two terms, numerator or denominator, we have to think of them as a grouping symbol. That's going to be important for how we solve this. This is the first time we've seen x in a denominator. So if that's ever happening, our goal is to get it out of the denominator so that we can solve for x. To do that, we'll just multiply this whole x minus 5 over. And then those cancel out, leaving us just with the 1. Here, we're taking this times 0, and anything times 0 stays 0. So there's no x left at this point. That indicates this is a no solution, or no x-intercept, so there's none. And I hope that makes sense to you. Think about this problem, what happened. Okay, we've been drawing the translation after we did it. We decided at x equals 5 was our new vertical asymptote. And we decided there was still one at y equals 0. Okay, so on this side, following the asymptote, we know we have to cross the y-axis at some place. We did it at that 0, negative 1/5. And over here, we just follow the asymptotes. We never crossed over that x-axis since there was that asymptote happening. All right. What you're always welcome to do on any of these is type them in your calculator to check them. But again, just like what we did here to solve, anytime you have two pieces, make sure when you're typing that in, you're using grouping symbols. All right. Please, if you have any questions while you're doing your homework, stop in to ask.